process does use an electric arc, but there's no slag that's produced. You've got an inert gas that's used in order to prevent molten metal from oxidizing. So you've got a cylinder of gas that provides a stream of that gas onto the work surface as you're welding, and that prevents the oxygen from coming in contact with the work surface. The electrode that they're using is also carries current, but it's not consumed. The electrode is made out of tungsten. Tungsten is one particular metal that has a high melting point. So we don't want it to be consumed in the welding process. We just want it to serve as a current carrier. You're going to have to also generally have a welding rod that you're going to use as a reinforcing rod in order to build up the weld bead. So in some respects, I guess it's kind of similar to oxyacetylene welding, but it also is an electric arc process. So the electrode is not consumed. It's not like stick welding where the electrode is actually consumed. The electrode only carries current. And you're going to have a reinforcing rod that builds up the weld bead, just like you use in oxyacetylene welding. TIG welding is primarily used for aerospace parts in particular. If we have specialty metals like stainless steel, Inconel, some aluminum alloys that are weldable, a lot of materials that would be not weldable with other processes, TIG welding is probably the preferred process for welding. If you desire to learn TIG welding, the Community College District, the continuing ed program here, has a good school for teaching TIG welding, as well as Palomar College. So if I had to learn one particular specialty type of welding process, probably would be TIG, because a lot of the aerospace metals that are weldable, TIG is probably the preferred process for doing it. To kind of give you an idea of why it's used, it's a big advantage in the old days when you had to weld aluminum, for example, with oxyacetylene. You had to use a flux, and the flux was difficult to see through when you're welding. This process does away completely with the flux. You can actually see the molten puddle as you're welding, so you've got a very clear view of what's happening during the welding. All you've got is a covering gas that protects the weld from oxidation, so it works really well. Additionally, if you have metals that would oxidize really quickly with heat, it's a better type of welding process. Aluminum oxidizes really fast, so when you expose it to heat, the oxide film will impair fusion. With stainless steel has got a real problem with expansion. And with TIG welding, you have such a controlled amount of heat that can be applied. You don't have to worry too much about expansion and contraction from applying too much heat to the work surface. So very controlled. Turbine engines, sometimes components are sometimes repaired by TIG welding, and that's it. The power supply is similar to a stick welder. It's a constant current power supply, but you're going to need some other attachments that go onto the machine to make it work. You're going to need a timer that times the gas that's coming out of the cylinder, and what that does is it allows the tungsten electrode to cool itself after you stop welding. If you don't have that, the tungsten electrode will eventually oxidize as well. As a matter of fact, one thing to kind of look for when you're TIG welding, if the tungsten electrode kind of turns black, it may mean that you've run out of gas in the cylinder, because you needed that gas to not only shield the weld, but you needed the gas also to protect the tungsten electrode. So, but you're going to need to, even after you stop welding, the electrode is still hot, you're going to have some gas flowing in order to protect the electrode from being oxidized. You need cables, just kind of like what you need for stick welding. You're going to need a shielding gas that's regulated in cubic feet per hour. And the machine is kind of special in maybe one way. In order to get decent TIG welds, they use an oscillating AC circuit. So it's got a high frequency pulse that's kind of identified with the sine wave that's used. What that does is it keeps the arc really stable. Also, there's some very nice equipment out there that will produce a square wave where we can alter the sine wave that's being produced in welding, and we can control penetration. We can also control the other factors in the weld a lot better than what we could do in the past. So there's some specialty equipment out there that was really nice. We got rid of our two water-cooled TIG welders last year, and it's been replaced with a one-thing-does-all type of welder. But those pieces of equipment were actually pretty good. You could weld, I don't know, maybe 16th-inch thick material without too much damage of going through or ruining the part, but still required a little bit of practice to do it. Also, too, dark coloring clothing, if you're going to be TIG welding, is kind of a nice thing to have. It reduces light reflection. Cotton clothing is generally deteriorated by UV, and if I'm welding, again, what I would prefer to have on would be probably a welding jacket. Again, you'll see some people use a cotton type of coverall when they're welding, but eventually understand that the UV will eventually break that cotton cover down pretty quick. The TIG welding setup, this is just a generic picture of what's kind of used in TIG welding. You're going to establish the arc with a tungsten electrode, and coming out of a torch assembly out of the nozzle, you're going to have an inert gas that shields the area that's going to be welded. The thing that makes it kind of common or similar to oxyacetylene welding is the reinforcing rod. When you're welding and creating the arc, you're going to have to kind of dip the rod into the puddle that's created in order to build the weld bead up. So it's somewhat similar to oxyacetylene welding. But you are really creating a crater, just like in any electric arc process. And so it has some things that are kind of like stick welding and some things that are kind of like oxyacetylene welding. You're going to need to regulate the gas, and you need to regulate the flow of that gas that's going to the torch. Some of the power supplies are provide for liquid cooling of the torch assembly. Some of them are air cooled, and maybe a little bit more of a complication if you've got a liquid cooled type of TIG setup. Here's one that's this one is liquid cooled. Here's one that's mounted in a truck, but it's kind of for on-the-fly type of welding. Tungsten electrode, usually you've got a tungsten torch assembly. They've got a collet that's beneath this gas nozzle, and then they've got a collet assembly that kind of pinches the electrode in place. And then when you screw the back half on, it pinches the collet onto the electrode so it doesn't back out. You've got maybe a better view of kind of what it looks like. But you can see the collet here. You can see the tungsten electrode here. The collet, it kind of grips the electrode. When you put the back half on, it pushes on the collet and squeezes it so that the electrode is kind of out of position. That's kind of how it's assembled.
So that electrode
Not consumer. Now, what I would tell you is, in minute amounts, the electrode is in fact worn away. So that's kind of what you've got. Here's a pretty good picture to show you kind of a cross-sectional view. So to kind of assemble the torch, you take the cap off, the electrode goes down into the split collet, and then we fix the electrode so there's a certain amount of stick out. And then when you turn the back cap on, what it does is it squeezes the collet around the electrode so it won't come out. The shielding cup is usually made out of ceramic, a ceramic cup. And then the gas that's going to be flowing from the gas supply that's regulated comes out around here. There's usually a gas lens also that has got holes in it that permit a certain amount of gas to kind of come through. If it's a water-cooled type of torch, you've got at least a 1 feed in for water and another feed line to allow the water to come back out of it back to a pump. Really, they call it water-cooled, but it's not. It's really a type of oil that's used in the torch, or as a coolant. It's a special type of oil. But anyway, that's what they do for cooling some of the torches anyway. And that's it. This shows you kind of a close-up view of what they use to adjust the pressure and the flow of the inert gas. The gases that are commonly used are argon, and they'll sometimes use helium, or sometimes mixtures of the two. They've got different characteristics. Sometimes people prefer to use argon because it's a heavier gas. So if you're welding maybe in a drafty area, thick. You want to kind of think of it that way. Sometimes helium is used. It'll give, when you use helium as a shielding gas, the arc is easier to go through. The characteristics of the gas are just thinner. But we do have to regulate the flow of gas anyway. This is the interesting thing about TIG welding. The properties of the penetration and the deposition, or I should say penetration and wide width of the bead are different than what you have in stick welding. In the case of DC negative, direct current electrode negative, this would be straight polarity. This, in fact, gives you the greatest amount of penetration in the work. There's ions, or I should say electrons, have gained an electron in their shell, and what happens is you've got greater amount of penetration in the work surface. And then there's also the gases become ionized in this process, and the gas flow also picks up a charge that's positive. The net effect of that is that 70% of the heat that's generated for any particular amount of current is helping to produce a great deal of penetration of the work surface. In the case of setting the machine up to reverse polarity, the electron flow is up from the work surface to the electrode, and the gas flow, which is now ionized, is kind of bombarding the work surface. In this case, you're going to end up with a kind of a wide bead, and 70% of the heat is really kind of concentrated in the tip of that tungsten electrode. We seldom set up the machine for reverse polarity, and I'll explain why later, but basically the problem is so much heat is generated in the tungsten electrode, there's the danger of actually melting the electrode off and having it fall into the molten puddle. So we would prefer for most welding, we'll either weld with straight polarity or we'll weld with AC. In AC welding, the machine reverses its polarity automatically at a fairly high frequency. It might be happening, the oscillations might happen on 400 cycles per second. So it happens really quickly. It'll give you kind of a compromise of bead, or at least a weldment. It'll give you some penetration to the work surface, and it'll also give you a bead width that is not quite as wide as reverse polarity, somewhere between the two. So that's it. Now, one thing that I can tell you about straight polarity, probably the most common polarity that's used for welding anything. For welding steel, alloyed steel, stainless steel, silver, which can be welded, copper, brass, titanium, cast iron, about 2/3 of the heat that's generated goes to the work surface. And that's kind of what we're trying to do with TIG welding. You still have to pay attention to the current you're using? The answer is yes. So we set the machine up for a certain amount of current, but 2/3 of whatever heat is generated goes directly to the work surface. Only 1/3 of the heat is reflected back to the electrode. The ionized gas is upward toward the electrode. Okay, so that's what happens with straight polarity. The electrode is negative. In reverse polarity, the electrode is positive. This is rarely used. Too much reflected heat back to the electrode. Remember what I told you. The problem is that there's the potential of already melting the electrode away, and it falls into the molten puddle, and then it contaminates the weldment. So again, we try to avoid that. If you do use reverse polarity, you're going to have to select a really big electrode, and that's required in order to absorb the heat that's being generated. And even though a third of it is going to the work surface, 2/3 are coming back to the electrode, which might tend to melt it away. So again, kind of the reason why we want to do that. There's one saving grace, though, in welding with reverse polarity. It's that ionized gas. The gas, when it becomes ionized, works to bombard the work surface and works as a cleaning agent. This is kind of desirable, but I don't know that it completely outweighs the advantages or the disadvantages of using this particular polarity. So there's one thing that does happen. The gas is actually lost one of the electrons. It becomes positively charged. That picture. In this case, so see the ion flow. This is actually the gas that's coming out of the torch. It loses an electron from one of the shells, and it becomes positively well, what if we set up the machine to AC? Well, if the machine is set up to AC, you kind of have the advantages of both polarities. You don't have as much penetration into the base metal as you do with straight polarity, but you don't have the problem of potentially melting the electrode off with reverse polarity. So what this does is it allows you to kind of get a compromise in welding. What this does is it's great for welding, particularly aluminum and magnesium. Aluminum and magnesium generally oxidize really quickly. If you just clean aluminum, within about 20 minutes of cleaning, in most cases, there's already an oxide film that's building up that will kind of impair fusion. So same thing is true with magnesium. They're just natural metals that oxidize without too much additional anything happening to them. What we'll do is we'll use half of the alternating cycle in order to produce the penetration. The other half of the alternating portion of the cycle and current we're using for reverse polarity, which will help to ionize the gas and feed it to the work surface for cleaning. So it's probably best used for aluminum and magnesium when we weld. You also have to have high frequency stabilization when you weld with AC. The arc is just, if you were to use like 60 cycle AC current, 60 cycle voltage, the problem is the arc is really unstable. The machine has an oscillator in it that produces a high frequency, maybe something like 400 cycle. This is a chart that comes right out of the 4313, and what it's telling you, if we're welding particularly magnesium or aluminum materials, what's probably preferred is going to be alternating current. And again, the reason is we can't set up the machine for a welding process that might cause the electrode to be consumed in the process or melt off or fall with the puddle. But we have to have a decent amount of penetration as well. For stainless steel, occasionally, or I should say for some stainless steel, low carbon steels, sometimes they set up for straight polarity. Again, reverse polarity, you can see here, not so good. Very seldom is this recommended for welding and TIG welding. You just don't do it. Not good. There's a lot of different types of tungsten electrodes that are out there. Some of them have a cleaned and a ground finish. The clean ones aren't really expensive, but the ones that are ground with a ground finish on them are really pricey. If you want to see what they cost, just Google gas tungsten arc, or I should say TIG electrodes. So they're about twice as expensive as the ones that are clean. So where I can get maybe a box of 5 for $17 of the clean finish, you can double the price for the ground finish. Some welders prefer to use a ground finish on the electrodes because it provides better conductivity in the electrode holder, or at least the collet that supports the electrode. So you claim to get better work out of it. Also, something that you need to know too, you have to set up that tungsten electrode in the electrode torch a certain way. Generally, we want the electrode to stick out about 2 diameters and beyond the cup, and that'll allow you to at least get into some fairly tight corners if you have to weld. But you don't want the electrode sticking out so far that it provides for the shielding gas not to reach that area. So we're looking for about a 2 diameter stick out or so, and that's about all. So you have to point the electrode, and you also have to have a certain amount of stick out that's on it. The way that the tungsten electrodes are color-coded kind of identifies the type of tungsten electrode. There's a tungsten electrode that's got a green band on it, and that's primarily an unalloyed tungsten electrode that's got nothing in it. It's used mostly for aluminum and magnesium welding. And what will happen when you strike the arc, a ball will form at the end of the tungsten electrode. It's not alloyed with anything. Some people prefer to weld with a pure tungsten electrode because they claim the alloying elements that are in some of the other types of electrodes can contaminate the molten puddle. True or not, again, that's what they prefer to do. Because it's got no alloying element in it, it'll just form a ball at the end of There's another electrode that's color-coded red. It's got a red band around it. That one is a 2% thoriated electrode. Thorium is actually a radioactive material, but there's only a small amount of thorium that's in it. The thorium is there to provide for the arc being stable, but you have to be kind of careful. When you have to point those electrodes and you go to a grinding wheel, the dust that's given off has got thorium in it. So you're exposing yourself to something that is potentially hazardous. So for this reason, there's another type of electrode that they call a lampinated electrode. It's got a different alloying element in it. It's not necessarily as hazardous. But you still see tungsten electrodes that are thoriated that are out there. When they are used, they're mostly used for welding steel. And because there's thorium in it, if you accidentally short the electrode to the work surface, there's less danger of contaminating the molten powder. So this sometimes happens, but again, will help to prevent the problem from occurring. There's another electrode that's got thoriated thorium in it, but it's only got 1% thorium. It's got a yellow band on it. It's a preference by some welders, what they prefer to use. And then there's another one that's got a brown band on it. It's got zirconium in it as an alloying element. It's supposedly a great electrode for, again, welding aluminum. Maybe better stability because it is alloyed with something that's in it. There's a lot of different types of electrodes. They're pretty much identified by a band on the electrode to tell you what is alloyed in it.
How do you properly dispose of thorium?
Well, the electrodes themselves, they're not a problem as long as they're in a solid state. The problem is the dust. So if it comes up, if it's vacuumed up and controlled that way, you're okay. In actuality, there's minimal amount of radioactive material that's in it. Even if you had a pallet full of the electrodes, it's not a problem. The problem comes in when you have to grind the electrodes and put a point on them. So that's where the dust problem kind of comes from. So you guard yourself when you have to grind it. By the way, too, when you grind electrodes to put a point on them, you don't take them to the grinding wheel and try to sharpen them like you do a pencil. The way to properly grind them is to put the grind marks that are longitudinal with the shank of the electrode going one way. What that does is it provides for better arc transfer when you do that. The magnetic lines of flux that are created when you try to grind the electrode in a circle around you try to take it the wheel and kind of grind it, around the circumference. You don't want to do that. You want to grind it so the grind marks all go along the length of the electrode. Shielding gas, you have to have shielding gas to protect the molten metal. So either argon, helium, mixtures of argon and helium are sometimes used. Some preferences for some welders that are out there. Helium, it's really light. The advantages, if you have to weld things that have a lot of thermal conductivity like copper, the arc can penetrate through that shielding gas really quick. So it's easy to go through. It provides, it gives you much more heat that's available in the work because the gas is kind of thin. I guess that's the best way to kind of describe it. If we're welding with argon, argon is used commonly too, but it gives you a quieter arc. Generally, a lower cost. The gas is a little bit cheaper than using helium. It's got better cleaning effect when it's used with AC. If you have to do aluminum or magnesium, it'll tend to drip less from the welding. So if you're welding out of position and you have to kind of keep the gas in one place, it's probably a better choice of gases to use. That's what I can tell you about argon. Gas mixtures, sometimes they have trimixes of gas, sometimes three different types of gases that are used. They sometimes even use a small amount of hydrogen, which is not really an inert gas, but if they have to increase the heat value or the heat of the weld, helium, or I should say hydrogen, is actually a flammable gas. So it's one way to kind of get a little bit more heat in welding. They only use that with mechanized welders and TIG, though. I've never seen that done with a hand-out or a bench-type setup with a TIG welder. starting and breaking the arc, this takes a little bit of practice. Some of the newer machines are easier to get the arc started with. Some machines, though, you actually have to start by tapping the electrode on the work surface. And what some welders do is they've got what they call a starter tab, which is a piece of metal that rests right next to where they're welding. So they get the arc started on that and then quickly shift to the area that they're going to be welding. So what it does is that if there's any burn through or there's any problem in the weld, they can kind of get that figured out before they move the torch to the work surface where they want to actually weld at. When you want to break the arc in welding, you just have to turn the torch at 90 degrees and then the arc is broken. So you start, you swing the arc into the starting position, and then to extinguish the arc, you can kind of break it away. Most of these setups also can vary the current you set by a foot pedal control or a remote contactor. So this kind of works like the accelerator on an automobile for a car. So the more you step on the pedal, the more you change the amperage, you increase the amperage. So we can vary the size of the puddle that we're creating within the range of the amperage that we've selected on the machine. So we can adjust it to a degree. Initial start, usually you have a little bit more amperage to begin, and as the arc is established, you kind of back off on the pedal in order to control the puddle. The process is kind of like oxyacetylene welding. Once you get the arc established, you're going to dip the rod into the puddle. Then you're going to release a little bit of the pedal, and then you're going to move the rod away. Then you're going to put the electrode back into position again and then step on the pedal. Then add rod to that molten puddle. So again, it's similar to oxyacetylene welding, but again, you're controlling the current pretty much by the foot pedal control. And that's how it's done. When we had more time in the semester, occasionally I'd let students play with our TIG welder, but now that we're reduced to 16 weeks, it's kind of tough. I mean, there's hardly any additional time to do anything. I had more time with an 18-week semester where people could try their hand at a little bit of stick welding, a little bit of TIG, but again, we just don't have that advantage that we once had before with an 18-week semester. One more welding process I want to make you aware of is called MIG welding. This welding process uses a wire feed type of mechanism to short the welding wire against the work surface. Here's a sample of what I did in 1988 with MIG welding. I took that class at City College, and in order to conserve material, they used a wire welder in order to build up welding bead for a fillet weld. So here's a bunch of MIG welds that have been created on a plate. Obviously, you don't need to have that much of a weld, but again, to save material, this is kind of what they did. This process is also an electric arc process, and it uses a wire that's short-circuited against the work surface in order to create the molten puddle or the heat necessary for welding. The gas that they use in MIG welding is usually a mixture of two gases. Sometimes they call it MIG mix, and what they're using is a mixture of 75% argon and 25% CO2. CO2 isn't necessarily inert, but it seems to work really well for MIG welding. The other option that they might use is carbon dioxide in and of itself in a MIG welder. The power supply is also different from what you'd find in a stick welder or a TIG welder. They use a constant voltage power supply. And we can also swap the polarity, but very commonly they just leave it set to one more polarity setting of whatever is considered to be most popular, what they want to use. There's something at the bottom that I want you to remember in MIG welding. I learned to MIG weld without any instruction. I just trial and error until I finally got it right. And one day, somebody gave me a helpful aid in order to kind of determine whether or not the machine's been set up correctly. If you set the correct voltage on the machine and the wire speed, you're listening for a particular tactile sound that kind of indicates that everything is going correctly. The sound that you're kind of looking for is the sound of sizzling or frying bacon. Once you hear that sound, the machine is set up pretty well. So once I had that in my memory bank that was a kind of an aid, everything kind of fell into place, particularly really only a couple of controls on a MIG welder you have to adjust. One of them is going to be a wire speed adjustment. That adjusts how quickly the wire shorts against the work surface. The other control on it really adjusts voltage control. It controls maybe the width of the bead. That's about all. So that's it. Things can generally go wrong too. Sometimes you'll end up with whiskers at the end of the weld. That's the unfused wire. If you look at a lot of MIG welds, the kind of telltale sign that's been welded in the MIG process, look at the very end of the bead. If you see some unfused metal here, we call it a whisker. And usually the metal has been welded with a MIG welder. I used to tell students also that MIG welding is never used on aircraft. That's not true. If you look at the kit box aircraft, one of the experimental aircraft, you'll look very carefully at the fuselage. It's made out of tubular steel, truss constructed steel. It's been MIG welded. You can see some of the wire whiskers that are left over after welding. So you know it's been MIG welded. Yeah, that's by the way, that's Wheeler North's old airplane. So yeah, so if you look at that, it's been MIG welded. MIG welding basics. I don't know what I can show you about this. Let's see if I got a little video I can show you. It's a quick and dirty process for welding. If you have to weld something kind of fast, it works.
These are selected scenes from the 70-minute-long MIG Welding Made Easy 17 video. Check out all the Quabell DVDs at quabell.biz. Hi, I'm Ron Quabell. I've been a metal fabricator for over 40 years, for nearly all of my projects. Today we're going to explore MIG welding, which is far and away the easiest type of welding to learn and the most popular welding process worldwide. Any welding process requires focused heat, and with MIG welding, the heat comes from an electric arc. The beauty of the MIG process is the filler metal is added to the weld continuously, while the weld area is protected from the atmosphere by a gaseous shield. It's a fast-moving process that's easy to control and easy to use. Most people learn MIG welding more easily than any other welding process, and that's one of the key reasons it's been so readily adopted by small shops and hobbyists. So here's what we're looking for: a weld bead that's evenly rounded, that blends in nicely to the base metal, and that has good penetration. I recommend that you make quite a few practice beads just like this until you're comfortable with the process. Now let's talk about some of the variables the operator can control. The circuitry of the machine always keeps the arc length constant, but by pulling the gun farther away, the stick out gets longer. The longer the stick out, the less current is put into the base metal, and you'll tend to get a tall, ropey weld bead that doesn't blend in well with the base metal, and the weld may have poor penetration. You also lose gas coverage as the stick out increases, which could cause porosity or contamination in the weld. The travel angle is important too. 10 to 15 degrees is the angle I typically use. If the gun is held more vertically, you'll get a flatter weld bead. The more you angle the gun, the more the weld bead will increase in height, and you'll increase the stick out too. It's easy to overdo the travel angle, so whenever possible, stay with an angle no more than 15 degrees. The speed you move the gun is an important factor too. This is one of the key areas for you to develop your own style. Experiment with the travel angle and travel speed to find out what gives you the best result. As you move the gun faster, the weld bead has less time to develop diffusion, and you'll get a taller weld bead that may not blend in well with the base metal. Moving too slowly tends to build up an excess of material in the weld bead and reduces your control of the puddle. Now we'll look at an application that MIG welding is very commonly used for: putting patches on automotive body panels. This fender's off a 57 Chevy, and the problem is that it has rust damage on the bottom and a poorly made previous patch. Okay, I'm ready to tack weld the patch panel into place now. So I'm going to go all around the edge of the panel, making tack welds spaced about 1 inch apart. Now we're ready to finish weld. And we have some options here. I have a couple of sample panels, and these have been welded in different ways. This panel has been welded continuously, and this panel has been welded with a series of tack welds. Let's look at the back side now. Looking at the back side, you can see I have excellent penetration on both pieces. But what I really want you to look at is the width of the discolored area. This is what we call the heat affected zone. You can see that the heat affected zone of the weld made with a lot of spots is about half as wide as the heat affected zone of the continuously welded seam. Warping is caused by the metal shrinking in the heat affected zone. The smaller the heat affected zone, the less warping you get. So I'm going to start adding on to each of the tack welds that I have. I'll make a weld about 3/16 or 1/4 inch long, adding on to each of these tacks. And after I've gone over each tack, then I'm going to stop and let the panel cool before I come back to add more weld. Okay, so we have the weld sanded completely flat, and as you can see, this really does make a beautiful repair. Some of the most challenging joints to weld are at the intersections of round tubing. A joint like this can be viewed as a fillet weld in one area, which makes the transition to a lap joint in another. Also, you want to keep the gun angle equal between the faces of the tubing as you're welding, while keeping the travel angle around 10 degrees. It takes a lot of practice to keep your motions coordinated when navigating a complex joint like this, but the more you do it, the easier it gets. Let's get set up to do some welding on aluminum. I'll be maintaining the 45-degree work angle and the 10 to 15-degree travel angle as I make this weld. Okay, so there's our finished weld. I'll spin this around so you can take a close look. Notice how clean and free of defects the bead is. This is a real boon for people who do a lot of welding of aluminum plate, such as building boat hulls, tanker trailers, and many other types of industrial fabrication. There's a little bit of soot on the weld, but that cleans right off with a wire brush. I'm confident that you'll have fun as you explore the world of MIG welding, and I hope you're eager to get started. So until next time, this is Ron Clavell.
Makes it look easy, but it's not. Take a break. I'm sorry? I'll see you back in about a half